Yeah. Thanks. So yeah, this talk is about fine-grained cryptography. It's probably going to be a bit all over the place, so hopefully it will be interactive, but that's kind of up to you. And I'll try to keep it relatively light, but maybe I won't succeed. There will be a lot of definitions, and like things will be changing all the time. So if you stop paying attention, you can just tune in a couple of minutes later. You'll be fine. Okay, so fine-grained cryptography, or how to do cryptography even if cryptography does not exist. It's not working. Okay, so yesterday we heard about some progress, I guess, in trying to prove a sort of cryptographic dream theorem, right? Either P equals NP or one-way functions exist. And right, this really would give an amazing win-win because, right, fast SAT algorithms could be potentially transformative in society. And right, cryptography has already been transformative. But unfortunately, as was highlighted yesterday, there are many sort of known obstacles to proving such a theorem. And still, like to this day, right, Impagliazzo's 5 worlds still remain separated, although maybe this will change in the very, very near future. I'm not sure. But right on just to sort of go through this again, right? In the one hand, we have P equals NP, algorithmica. I just sort of made these pictures. Heuristica, where you can't solve on the worst case, but natural instances are easy. Here, natural instances are hard, but cryptography doesn't exist. Mini-crypt. We have one-way functions, symmetric key cryptography, all sorts of things. Cryptomania, which is, I guess, loosely defined to be public key exists, and potentially much more. Public key cryptography exists. And so sort of one motivation, at least, for looking at fine-grained cryptography, or a number of motivations, is maybe we can hope to circumvent these barriers by is there some way to circumvent these barriers? I haven't said what fine-grained cryptography means yet. And another sort of motivation is like maybe we want to recover some sort of security, even if we're in sort of one of these bad worlds, like heuristica or algorithmica or Pesiland. So can we hope to recover some notion of security? Because right, without security, our society would collapse, basically. Okay, so the approach we take in fine-grained cryptography is very naive or natural, I guess, depending on how generous you're being. So right, what do? We refine the adversarial model, or right. So right, classic cryptographic adversaries. Right, they run in arbitrary polynomial time where you're not fixing this polynomial ahead of time. And fine-grained cryptography, or at least I guess in the sense of fine-grained cryptography that I'll be discussing today, we're going to just crop the running time. Okay, so now potentially, right, P equals NP. It might be that P equals NP, but the SAT can only be solved in n to the 100 time, right? Which is, I guess, not very useful, probably, but it means that we can still hope to potentially recover some meaningful notion of security. N to the 100 time is incredibly infeasible for n equals 2, right? It's already infeasible. So maybe there's some hope here, and maybe this sort of classical dichotomy leaves some room to maneuver. I guess this is the big point. And so yeah, bounding the running time is one notion of considering fine-grained cryptography, and that's what sort of I'm going to be focusing on here. But right, there's other notions of bounding adversaries that you can consider and have been considered. So you can consider sort of logarithmic space adversaries, other classes within P, NC1, So sort of very efficient parallel time adversaries, or even AC0 adversaries. And as you get lower, right, as you get to AC0, maybe you have some hope of getting very strong results, unconditional results. Say more about this in a second. I should mention sort of two other models that have become incredibly important, I think, in the practice of cryptography in recent years. And so one is sequential time. So here you have an adversary where you're bounding the number of sequential. So you're bounding the number of sequential operations, say by some fixed polynomial, but sort of you can have arbitrary parallelism. You're not bounding the parallelism. Sort of a converse model is sort of your bounded space. So where you're bounding the sort of space complexity of your adversary, but maybe you give him relatively unbounded time. Yes.
When you talk about bounding the adversary, the good guys will always be even more bounded?
So, okay, I'm going to discuss sort of different regimes. So this is like, I guess, is this my next? The cryptographic regime is exactly what you're describing. So in the cryptographic regime, sort of, in the cryptographic regime, this is like right where the honest party is very weak, and he's trying to fight against this very strong adversary. Maybe not classically, not quite as strong as the classical adversary, but still much, much stronger than he is. What did I want to say? Right. Else, but before we get into the weeds, so in this talk, I'm just going to focus on end of the C adversaries. I'm not going to be very specific about what this means. You can think of it as a circuit of size n to the C, or whatever. Yeah, so maybe that's the best model. And okay, and maybe some more reasons. So okay, so maybe you want to get around some barriers. You want to prove stronger results, I guess, or I don't know, show that cryptography is possible in these worlds. But there are other maybe motivations, even if you believe that one-way functions exist. Why would you want to weaken security? So one reason is it gives you a potentially new sources of cryptographic hardness. By considering sort of new problems that maybe are not even super polynomially hard, but maybe robust against, say, I don't know, new attacks. Right, the sources of, say, post-quantum hardness are relatively few and far between. Another reason is maybe you can get more efficient cryptography. Cryptography is expensive, particularly public key cryptography, and especially as you get fancier and fancier, it gets more and more expensive. Maybe if you consider a weaker adversarial class and don't worry so much about super strong adversaries, you can get something that's more concretely efficient. And the final reason, I guess, that I have on this slide is sometimes it's necessary and sometimes it's actually what you want. And sort of we'll get to this later on, but yeah. Okay, so first the cryptographic regime. Right, so here we're going to think about sort of scaling down classical cryptographic primitives. So here is a sort of very incredibly informal definition of a fine-grained one-way function, or like what I would call an n-squared hard fine-grained one-way function. Sort of I want you to keep in mind, I guess, for this talk. So right, we want a function that you can compute in sort of the forward direction. You can compute f of x in essentially linear time, but it should be hard to invert in, say, quadratic time, strictly less than quadratic time, let's say. Okay, and this is sort of this formalism that I have here. So right, what are we saying exactly? So strictly hard to invert in quadratic time. What do we mean is it's hard to shave off an arbitrary polynomial factor. This is sort of what we're going to mean by hard to invert in subquadratic time. And where does this I guess I'll say in a minute where this comes from, but just as a quick sanity check. So, right, we relaxed this notion of security. sorry, my slides here not matching my computer anymore. I'm not sure what's going on. So right, just as a quick sanity check, is there any hope of like making by this relaxation we get unconditional security? No, or probably not, because right, this will give you polynomial bounds on SAT. So, but right, is it possible? Yes, because right, a one-way function, right? We just have this sort of weaker guarantee on that. We just care about this weaker guarantee. So a one-way function, of course, satisfies this definition. Okay.
Why not this linear quasi-linear time?
You can do complexity leveraging to get it. Yeah.
Why is it a sanity check? What if it was possible to do unconditionally? That would be even better.
That
Why would it
would be better, but I'm just trying to make sure that it's like we're not dreaming too big, I guess. Right? We did something very simple to try to get around these barriers. It's not going to solve all of our problems, I guess.
I'm trying to understand what the sanity check is. NP is not in quadratic time already.
So I think you mean like n time order n.
Maybe
Not
Circuit size. They replace lead time. But
Yeah, sorry. Yeah. Circuit size.
Do we have any candidates for this function, which are not just one-way functions?
Yeah, I'll get to that in a second.
Thank you.
Yeah. So yeah, maybe I'm not stating this correctly either, though, right? So you can think of a parameterized version, right, where like you're not going to be able to speed it up. Yeah.
It's like no basically.
Yeah. Okay. All right. So what is the sort of, so I guess where is this epsilon coming from? So what is a potential place where you might hope to mine assumptions, I guess, to build these primitives? And this is a fine-grained complexity. And so this fine-grained complexity, at least my understanding of it, was born out of this observation that for many natural problems, brute force or something essentially close to brute force was essentially the state of the art. Okay. Maybe, I don't know, Russell or Ryan can say something different.
I think it's more, I mean, in general, not necessarily brute force, but whatever algorithm we came up with 50 years ago.
Yes. Okay, sure. Yeah, I guess I'm going to talk about some examples where brute force is not the best, but it's not.
We've been doing it for 50 years also. Not only 50 years.
But not me personally.
Close.
Getting closer.
Okay. So out of this, sort of a theory was developed, this sort of theory of fine-grained complexity. So right in the theory of, say, NP completeness, the sort of tool that you're using is so right, what do you want to, so this theory says, like, right, theorems of the following form. If you can improve the exact complexity of X, where exact means improved by a arbitrarily small polyfactor, then you can improve the exact complexity of Y. Okay, and sort of the tool here is this notion of a fine-grained reduction, right? The reduction that preserves the exact complexity of the problems. Right, so the analog, right, this is not like a polytime reduction, because a polytime reduction might eat all of sort of the exact complexity in it. So you have to be very, very careful here. We'll see maybe an example, or we will see an example at some point, but and this theory sort of led, so as soon as you have like theories of dependencies and all of these problems, right, these problems where there's been sort of no algorithmic progress for 50 years, led to sort of conjectures for many natural problems, and natural, like, interesting problems, I think, that are important for data science and stuff like this, that, okay, maybe not brute force, but something relatively simple is essentially the best thing that you can do. Okay, so right back to the previous question. So what sorts of things that imply these fine-grained one-way functions, but are not one-way functions? And so, right, so disclaimer, like neither of these are particularly interesting in some sense, but I think that it's worth sort of looking at because it's not clear that they imply one-way functions. So for example, the planted k-clique conjecture. So this says that if you take a random sparse graph and you plant a clique of size k somewhere in it, it should take essentially n to the k time, right? Essentially enumerating overall possible cliques to find this clique of size k. You can do better?
Yes.
Okay, then
To the
maybe.
omega k.
Okay,
Which
right.
is
Sorry. That's true. Right, sorry about that. And then, for example, another example is the k-sum problem. So k-sum says, right, if you're given n integers, think of these as very large integers, and some target t, such that k of these numbers sum to t, find this subset that sums to t.
Or should we say what sort of range of k?
K, right. In both of these problems, think about k as being a constant.
If a planted k, what will the distribution be? I mean, if it's the random graph.
Can you repeat the question also?
How does
We
the graph
didn't hear
just-
the question.
Yeah.
So Raul is asking what the graph would be. I don't have a good.
Is this worst case or average case?
This is average case, so there it doesn't. Yeah, it's like two. Yeah. This is very. Okay, so right. So there's a lot of this. Let's ignore the top line. Here's a conjecture that works. If you think about, for example, so you can think about some notion of the zero k clique, which is sort of a combination of k clique and k sum, and this I guess you can know this. Sorry. Yeah.
You said something about maybe this is not an interesting example.
Right.
I wanted to ask, how can something, like, isn't it interesting by virtue of implying a fine-grained one-way function, or how do you judge interest?
I'm saying this is not interesting because the assumption is already, you're assuming it's one way. Okay.
Oh, the
So right,
proof
let's
of
think
the
about,
statement,
let's just
the
focus on
conjecture
k-sum
already
because
gives
this is what
it.
I'm
I
actually
see
going
it.
to talk about.
I see.
So right, this, like the assumption that it's hard to find the set that this sums to is you're assuming that it's a one-way function.
I
Okay.
understand.
Yeah. So in this sense, it's not very interesting.
Like the theorem, this implies fine-grained one-way function, the proof.
It's like you already assumed it, but
I see.
Over some distribution that we haven't specified or.
I guess I haven't specified the distribution for k-sum exactly, but you should think of these integers as being significantly, think of them as like working mod p for p that's significantly greater than n to the k. And then they're just random numbers, and you choose a random subset of size k and plan to talk it.
And in the. How do you pick the random sparse graph?
I retract. I just did this late last night, and that's I retracted. Maybe. Okay. So right, as I said, these at least the second conjecture is not a very interesting way of getting to a fine-grained one-way function. So, but yeah, so given that this is sort of a meta complexity workshop, maybe one thing you might try to do is maybe try to characterize fine-grained one-way functions, or even find worst case hardness assumptions that that imply one-way functions, fine-grained one-way functions. So intuitively, maybe you could hope that something like time-bounded Kolmogorov complexity, if it's only weakly hard, like if you only assume it's hard against n squared time adversaries, maybe you can hope to get something. Although I think that this It's not clear that this will give a characterization. I'll sort of say why in a second. And the problem, I guess, towards sort of cut off, the problem with achieving such a characterization is that these fine-grained reductions are very delicate. So in a fine-grained reduction, we want to say, like, right, if I can improve the exact complexity of a problem A, then there's a reduction that improves the exact complexity of a problem B. But so let's think about the specific case where TA equals TB. Then you can sort of only make a few calls to the underlying solver for A, right? You have to make a sub-polynomial number of calls, at least if you're using it in a black box way. But that is, oh.
Yeah, I mean, you can call, so actually there's many fine-grained reductions which.
But yeah, you can do.
Make really small calls, a bunch of many small.
Yeah, exactly.
That's actually like the entire equivalence class. So
Yeah. Yes, yeah. But some sense in the cryptographic setting, if you're calling on like different parameter regimes, you need to be careful because you might be losing the hardness that you need. But yeah, absolutely. I'm just saying this is some sort of very bad intuition. And definitely there are ways around it. It's just how to do it it requires some thought. And in terms of like getting a characterization, this is why.
In some of these characterizations, we actually use exactly that trick that we call it a smaller inputs. So there's actually a big chance of.
Yeah. Absolutely. But I guess the issue here, and I say something in a second, but right, the issue is like it's not clear how to do like Hill, for example, if you wanted to use your right. And there's actually sort of, so this is just a very high level intuition for sort of one potential issue you could run into, but there's actually sort of black box barriers from Chris and Geoffroy showed barriers to sort of showing sort of at least amplifying going from average case hardness to fine-grained one ways. Okay, so so as I said, there's some potential problems. So one thing, for example, you might want to do, or maybe one so let's look at some sort of like classical mini crypt style theorems that you might want. So for example, one thing you might want to do is you might want to amplify a weak fine-grained one-way function to a strong fine-grained one-way function, right? So suppose like I can invert with, suppose I just promised that you can't invert with the constant probability, and I want to amplify this to say maybe just 1 over n, right? This sort of intuition from before is right in some sense, if you're making a black box reduction, to this A prime, you're going to have to make n calls. And right, this is I guess maybe Rudich's observation, right? There's formal barriers for hardness amplification in some sense, right? If you're only calling A prime on random instances, you need to call it at least n times to even expect it to work once, right? And the upshot of this is if this guy is running in, say, like just strictly quadratic time and you're making n calls, then all of a sudden, if you compose it with your reduction, you now have something that's running in cubic time. So you're not preserving this sort of, these reductions don't preserve the fine-grained time complexity, at least naively. So, but maybe there's better things.
Even like this, why are you so worried about a loss of one? Because if you have a gap of 100 versus n squared, and squared to n.
But maybe I want to study just like what's possible with n squared. Maybe right, I can invert everything in n squared time, and so this is the best I can do.
So you really want super tights?
Yeah, I think this is the interesting question. Yeah.
The natural examples where you stuck with the quadratic hardness and you cannot generalize the problem to the equations, and then the day before.
For a one-way function, so there are fine-grained problems that aren't as parameterized, I guess. It's potentially right. So the parameters for problems I showed before, like you can just keep scaling up the parameters. And some of them, for some problems, maybe you only have hardness for some way. A problem that's not parameterized in the same way. I'm not sure. I guess I'll say something later. I'm going to talk about proofs of work, and here there's sort of we don't know how to get super quadratic. But this is sort of a different regime. We still don't know how to get super quadratic hardness without introducing new assumptions to sort of kill the round. So yeah, it's a good question. Okay. All right. So another primitive you might consider, another fine-grained primitive, potentially a more useful one, is a fine-grained pseudorandom generator. So here, right, we want a generator that's computable. This is like a cryptographic fine-grained pseudorandom generator. So we want a generator that can be computed in quasi-linear time, but shouldn't be distinguishable from uniform in subquadratic time. So, right, can we hope to prove some theorem, some sort of version of Hill in this setting? And here's again sort of a very naive sort of problem here is like any PRG distinguisher is only returning one bit. And in some sense, intuitively, like to invert the one-way function, you need to recover n bits. This is okay. I'm not saying that this is always the case, that this is not a formal barrier, but this is sort of some sort of problem here, at least if you're trying to do something generically. And so it seems like some reduction is going to need to make n calls, right? There are formalizations of these, Trevisan and Gennaro and stuff like this. So there are formalizations of like sort of barriers here, right? And this applies like even if like you want just like, yeah, you start with a one-way permutation variant. Like you just want to cycle it, but yeah.
So I'm just curious, like, so do you think such a thing should be possible, and we just need to find the right technique, or you think they'll be like in this setting, these notions might be separated?
I think everything is possible. Yeah, but yeah, I'm sure like there's probably a way to phrase, yeah, to rule, yeah. So you can rule out certain kinds of deduction.
But there are some obfuscation-based counterexamples, things like reversions or exolemmas.
Exactly.
Imagine such contrived counterexamples.
Yeah, it seems possible, but maybe there's right for every function, maybe there is a reduction or something like this. Or I don't know. Yeah.
So. In regular cryptography, coarse-grained cryptography, we can generally have efficient constructions by making algebraic assumptions, right? Like not going via this reduction route, but making concrete assumptions. Like if I want a PRG in general, I don't think of first sampling, like getting a one-way function and then using that to construct a PRG.
Yeah.
Typically, for an efficient PRG, I'll make an assumption that will give me a PRG.
Yeah.
So in this fine-grained regime, do we also have different algebraic assumptions that some assumption may be sufficient, like it may be weak and give me a one-way function which can then give me a PRG.
Yeah.
Like another assumption which can give me a sufficient fine-grained PRG.
Yes. Great. You're leading me to my next. Just wait. I guess maybe a couple more slides. Okay. So right, this barrier at least, right? But the problem was right. You had to recover too many bits. But it's potentially possible. One way around at least this barrier, right? Recovering too many bits is that right? Maybe I don't care about all of the bits, or maybe the input is like I only care about sparse inputs. So there really aren't that many inputs, and I don't need to learn so many bits. And then maybe I only need to run in something, that's sub-polynomial in N, the input length. Okay, so where are we going to get fine-grained PRG, or one way to get one? is from this k-sum function. So this is just sort of rewriting the k-sum. This is like the one-way function that you get from this targeted k-sum. So you get a random, think about like these being random, random a, random x, and you output the numbers a, and the inner product. I guess I should have. Hold on, let me back up. So this notation, I guess what I mean, k, s, k, n. These are like k sparse vectors of length n. So they only have k ones. So when I take this inner product mod p, I'm just rewriting, summing up k of these numbers. Okay, so this is just the function, and so this is something we showed with Gal Arnon, Alon Rosen, and Prashant.
So you don't output n.
Is there?
Yeah.
You don't output
What?
You don't output n.
You don't know x.
You don't output n.
You don't. If you output x, it wouldn't be. So this is sort of like this is the sort of one way. This is why it's one way. So you don't know x. So
So to make a stretching, you need p to be much larger than
absolutely. Yeah. Right. You want to be in this sparse regime. So there's So in particular, if p, I guess I did it right there. If p is much larger than n to the k, then in this case, if I see something of the form a with a uniformly random element from fp, there's not going to be any solution of size k. Just by counting.
Why output in A if you not output A as well?
Then we won't have
It
structure.
does look a better set. So,
Yeah.
Yes. But if you assume large P, maybe drop A, maybe it becomes simpler to prove.
Maybe. Yeah.
So increasing the stretch is also hard.
Yeah. So you're saying if I want to compose a like in a generic thing, this is potentially problematic. So what is the theorem? The theorem says that assuming this function is fine-grained one way, then it's a fine-grained PRG. Or in other words, there's a search to decision reduction for this planted problem. If I can distinguish the planted distribution over here, I guess maybe I should be using enough. If I can distinguish this planted distribution from the unplanted case, where it's just a random thing, then I can recover the planted target X in a fine-grained way. So what is the starting point, at least, of our reduction? I should mention Prashant has a different way of doing this with his students, but I'm going to show you the way that I'm familiar with, at least. So the starting point is this classic paper from Impagos and Noor, and they showed us a search decision reduction for subset sum. And they're sort of, at least my idea of their sort of critical observation. So what they wanted to do is they want to reduce to the Goldreich-Levin predicates, and basically, if you just look at these things, they look very similar. The subset sum function is computing sort of this inner product where this, so let's think about subset sum, not k-sum. So this is just a 0, 1 vector now instead of a k-sparse vector. It's just computing this inner product, and over here you're computing an inner product, but z, I guess, is also 0, 1 valued, and this is mod 2, and this is mod p, but it's it's almost there. And so what did they do to exploit this? So what they did is they showed that if you could distinguish planted from random, then you could predict this Goldreich-Levin predicate, inner product 1, 2. Okay, so we want to build a predictor given a distinguisher. So the predictor is given z. This is what you're going to, you're trying to predict the inner product of x, which you don't know with z, mod 2. And you're given the output of this one-way function. Okay? So write this output of the one-way function. So I sort of highlighted in green, sort of what are the sort of numbers that are in the target. What did they do? So you have Z, they just sampled a random alpha from your field and hit Z with it. And then, so sum up the result that you get. So you get this new vector, I guess x prime or something. And the question is, what do you do with the target? Right, we need to output a new target. And what did they do? Well, they just sort of, what should the target be if we wanted it to stay planted? So we know that the target, is just the sum of these things. So so this element, for example, A2, will still appear in this target. This, if we think about sort of the new target, a new hypothetical target, this element didn't get an alpha. This one did get an alpha. All you need to do is count the number of alphas in the intersection of where Z and X, where both of them have ones. How many both have ones? What was their observation is you just guess this, It's a number between 1 and n. You guess it with pretty high probability. And and if you guess this, if you guess it correctly, then I add an m copies, the number of the intersection copies of alpha to the target, then I've this is exactly identically distributed to a planted instance. And if I guess it incorrectly, then I've multiplied alpha, which is just a random thing, by a non-zero number. This is just re-randomizes this completely. It's completely independent of whatever you started with. So it's exactly the random case. So now we can just use our distinguisher to check sort of approximately which case are we in. And if we think we're in the right case, we just output the parity of M, which is going to be the inner product, Assuming we guess correctly, this is just the inner product mod 2. And otherwise we output, it's independent, so it doesn't really matter. What is the loss? So their loss, the loss is going to be 1 over n, because it's just basically the probability that you guess correctly. Here, and in the k, sparse case, the loss is just 1 over k, because these are just subsets of size k, so you only need to guess a number between 1 and k. The intersection is at most k. So we're sort of halfway there, okay? So we're following the paradigm. So so we have a fine, this everything I just said to you is fine grained, this is fine. The problem is, so now once we have this Goldreich-Levin predictor, we want to use it to recover x. Okay? But Goldreich-Levin, which is fine, but the problem is Goldreich-Levin has at least n overhead in expectation. Or more if you want to do it exactly. So what do we show? Is sort of this simple lemma that if we only care about recovering k-sparse vectors, then there exists sort of this new predicate, which is going to be induced. There exists some matrix which you can find efficiently or sample randomly to do if you care about parameters. W, such that if I can predict this new predicate induced by okay, good. If I can produce how this new predicate is very similar to it's just a linear function again, but instead of a random z, we're going to sample a short random r, hit w with it to get a z and get yes.
So there's a whole mini area in signals processing about sparse Goldreich-Levin theorem, and I forget what they call it. Sparse recovery. Sparse recovery. Well, this particular for the, they think of it Fourier transform. Okay, it's still called sparse.
I think sparse recovery is a big umbrella.
So yeah, big umbrella, but it's
compressed sensing. What
that's over the reals. Compressed sensing is over the reals.
Right,
but there is a notion of sparse Walsh-Hadamard transforms. I'm not sure they give you exactly what we want here. I'm not sure.
This is list decoding, right? So
yeah. I'm not sure they have the list decoding. This is exactly the issue. But It's potentially possible that we're reinventing a wheel that another community
Yeah,
has
I
already
think you might want to look.
Yeah. Anyways, but the main point is that this is possible and potentially interesting. Right, so what do you get, right? You can recover this sparse X, at least, right? If I only care about expected running time, then it's going to be quasi-linear in K. Okay, so very fast.
But the main problem is this, you still have like epsilon squared dependence. So,
Right, so if you're running like K squared or K cubed time, then you can, you're gonna have an epsilon somewhere, I guess.
Yeah.
So either you're preserving the 1/epsilon. I mean, you're not gonna be able to improve the hardness basically. So either you need to pay for like a, right, 1/epsilon squared in your running time, or you need to pay for it somewhere.
Yeah.
Marshall, how do you choose W?
But the key point though is that the previous step doesn't introduce a big epsilon, right? It's just a 1/k loss. So whatever epsilon, if you started with a pretty good epsilon, then it's not much worse. What is, sorry?
How do you pick W? How do you choose W?
Choose W. We took something from, this compressed sensing literature. So this is combinatorial compressed sensing, or for all sparse recovery. You can, so the thing that works, and so you have to be careful for what works mod 2. But like sort of the simplest thing that I could at least understand was there's like a simple thing if you use like an unbalanced bipartite expander, and then you can construct this. Use it as like bit masking technique where you just output the sort of index. Okay, all right. So what is the high level idea? There's nothing complicated. There's nothing actually very complicated going on here. So right, what are we doing? Exactly what I guess Russell is saying, right? We're taking something from this compressed sensing literature that's tailored to this finite field setting, compressing X to be essentially as short as possible. Once we're in this small dimension, then we have time. We can actually run Goldreich-Levin because it's running in the dimension polynomial, say in the dimension, or in the way I stated expected time in linear in the dimension. And then this is a compressed sensing scheme which emits a like very fast reconstruction. That's where this is coming from.
So again, what is K? How small K can be?
K is, you should think of as a constant. Yeah, I know this doesn't really make sense to put K, but right, yeah. There's polylogarithmic factors and 1/epsilon, I guess. Okay. And the point being is like this, like the sparse Goldreich-Levin wouldn't be very hard. The important thing is like we needed this thing to be a linear predicate. This was really important for the previous reduction. And I guess I'm already out of time. I'm not going to get to the second point. But right, so right in the reduction, you should think of these Z's as chosen by choosing a random short R and hitting this matrix with it. Okay. So fine-grained, so that's sort of wraps that up. So fine-grained public key cryptography. So in this you can imagine sort of this is sort of an
Question. So maybe in some sense one assumption is not the right abstraction for fine-grained, right? Because the input is large, so no way you can construct with that. So
that's true. That's true.
Nothing smart to say.
Yeah. It might be just like sort of the wrong primitive to be thinking about. Okay. So what fine-grained public key cryptography. So here's, I guess, the definition of fine-grained key agreements. You have Alice and Bob. They're interacting. I guess you want, didn't write it. You want them to be running in, I guess, again, quasi-linear time, but you want them to be the key that they produce to be secret relative to Eve, who's running in, say, n to the c time. So we have a lot of sort of results here. So right, Merkle puzzles, like this classical notion from the 70s. This is a fine-grained key agreement with n squared. Right, Yuval and others showed that you can make it work with just an exponentially secure one-way function instead of a random oracle. In a very nice paper from Rio Levine, Lincoln, and Vasiliska Williams, they showed how to sort of adapt Merkle puzzles instead of relying on exponentially secure one-way functions, to rely on planted sort of average case hardness of either the zero-weight K-clique problem or the K-sum problem. I'm not going to say what zero-weight K-clique is. And they showed, right, I guess, like you have some sort of non-trivial advantage that approaches 1.5 as K grows. So from what I just showed you, K-sum sort of we know from sort of a classic or not so classical, but Lubachevsky and others, right? Given subset sum, you can show from subset sum, you can build public key cryptography. You can emulate Regev encryption in a very sparse regime. And so if you apply what you just saw, you'll get a public key crypto system for K over 2. And so this is a recent work of Prashant and his student, Saga Schwarzbach, and they showed assuming KXOR and LPN, you can also get a fine-grained public key crypto system. Yeah. Good. Yes.
How do you pick K?
How do you pick K?
Yeah.
If you're a practitioner, I guess you probably don't use these schemes. But right, K is what you're assuming, I guess, in some sense.
So
pick K to be large enough. Yeah.
What is the largest K that's reasonable?
Sky's the limit. I don't know.
I mean, certainly you can't go beyond constant, because at that point I have one-way function.
But because you do have one-way function if the problem is not.
Yeah. In some sense, it's not it seems unlikely that K sum is hard, but subset sum is easy. So maybe this isn't the greatest example. Yeah.
So all of these are the planted versions, right?
All of these are planted versions. Yeah. Or or the sparse. Yeah. Yeah.
Is the notion of security also kind of, because you have K, you have security parameter.
So here, I guess I'm thinking of the security parameter as n.
Yeah.
In all of this. Does this make sense? I mean, yeah, maybe you want to tune K and n, but you need to be right. There's like a mismatch, I think, between theory and practice. Yeah.
So are there any primitives we either can't get or know we can't get generally, but we can find cryptography?
Yes. So, okay, so you can build other notions beyond this of fine-grained crypto. There's sort of, I wanted to briefly touch on, so some other, in the complexity regime, you have an honest party that's much stronger than the adversary. There's sort of some examples, so I guess in de-randomization is sort of one example where this occurs, but there's examples where for security reasons, you're sort of forced into this situation. Maybe you would want to do better, but you can't in some sense, and particularly when you don't have like secret information and maybe you're trying to protect a key or something like this, there's sort of no hope. But yeah, back to your point, there's other sort of something that's become particularly useful recently, and I guess we already saw an example in this conference, is sometimes we want crypto that's not too hard to break. So this is sort of the very different. So this is sort of the mixed regime. We want a weak, very weak honest party who's maybe hiding behind a strong honest party and a slight, maybe nearly as strong adversary we want to protect against. So I don't want to define moderately hard one-way functions, but an example of this is a proof of work. right? Or a cryptographic puzzle is something we saw on Monday, which is sort of a proof of work without like a non-amortizability guarantee. So in this case, right, we want the prover to like be somewhat efficient. And we want to bound, but we don't want anyone like a cheating prover to be able to be vastly more efficient and still convince the verifier. And this is sort of very, very different regime. So yeah, and these sorts of things I'll just say is right. These sorts of things you can build from sort of worst case conjectures in fine-grained complexity. But critically, I guess, so back to something Yuval asked, or sort of like maybe an open question, particularly here, is without assuming cryptography, at least I don't know how to get a prover that, like, to get harness for provers that are running in, say, cubic time, and a verifier that's running in linear time. So if you want this sort of, so right, we can get quadratic gap. So right, it's quadratically hard for the prover and verifier. And if with interaction you can do better, but if you want it to be non-interactive, if we really want to just send a proof and be done, which is like in most sort of applications, this is what you want. I don't know how to get beyond this. But potentially there's some efficient batch verification that would at least get you to cubic or something. I don't know.
What I was trying to ask is there something that even if I believe in crypto, you can't get, but you would be able to get in the fine-grained sense? Because maybe it's impossible to get a separation that is non-polynomial versus polynomial, but you could get a separation between different polynomials for some tasks. So can you get black box obfuscation?
One example would be Merkle puzzles.
Yes.
So, so if you have like a very random linear time function, then you could use the Merkle key exchange to do key agreement in with n-squared security, but you can't do better than that.
I think he was saying if we forget about assumptions, that's the conclusion. I'm guessing you're on.
Yeah.
Because usually when we say that something is impossible to get, even if we assume cryptography, because of what type of statements we are trying to get, usually we mean that it's impossible to show super polynomial addresses, say for example.
Yeah.
Now we are satisfied with
so something more cryptographic flavored, you're saying, where it's like
get black box obfuscation, say if all I want for obfuscation is that it's n cubed R, not more.
That is a great question. I don't have a good answer off the top of my head.
That person is no.
Yeah. What? It seems unlikely because you can sort of leverage.
Very specific to, for example, yeah.
What did you say? What was the murmuring?
Can you get black box obfuscation?
No, I heard the question, but what was the answer?
No.
No. Yeah, I agree. It seems like I'm not sure about it, but it seems like the counterexample should.
Okay, I think we should take more some take more questions offline.
So you could like think of your sparse input.